Okay, so we were doing polynomials, right? What exactly is a polynomial, if you remember? How do you know if something is a polynomial or something is not? Let me just plug my pen. Do you remember anything about last week's stuff?
Kind of.
Okay, here's what it is. If you have x, okay, doesn't matter what the number in front doesn't matter. If you have x, and then you have this to the power of something, as long as this power is a whole number, okay, can't have fractions, as long as it's a whole number, that has to be greater than or equals to 0. So for example, x to the power of 0 is a polynomial, that's a 1. X to the power of 1 is just y equals x, a straight line, that's a polynomial. Then you keep going, right? x2, x3, x4, like that. You can go to like x 5000. So this power, as long as it's greater than 0, greater than or equal to 0, and a whole number, okay? Can't have negative. So like, for example, x to the power -2. No, that's not a polynomial. Is this a polynomial? 5 to the power of x. What do you think?
No.
No, it's not, because this is an exponential function. It is not a polynomial. Now, why are polynomials special? It's because they go on forever. If you look at x, this is x, right? Y equals x. If you look at x squared, the domain of any polynomial function. Domain means the possible x values it can take, okay? The possible x values it can take. The domain of any polynomial function is from -infinity to +infinity. What this means is that the x value can be anything on the number line, but the range is going to be different, okay? The range is going to be different. The range for an odd degree polynomial, what does odd degree mean? Odd degree means like x1, x3, like that. You see, this is the degree, right? So if it's an odd number, then it's an odd degree polynomial. The range for an odd degree polynomial is also from -infinity to +infinity. Like if you look at this, This point could be some value of x, right? -10,000, but also -10,000 on the y. If you follow this line, it goes all the way down to -infinity on the x, and then -infinity on the y. Same exact thing on the other side up here. So the range of an odd degree polynomial is from -infinity to positive. But the range of an even degree polynomial, it depends on its minimum value. Look at this. What's the range for this guy? X squared. So range means the possible y values it can take.
0.
Yeah, 0 to what? 0 to, for that one, is going to be 0 to infinity, okay? Because it can never be negative number. It has to be 0. Here's another idea. Well, this is just a notational issue. Can it be 0? Can it be exactly 0?
Yes.
Yes, it can. Okay, so if that means it's inclusive, okay, inclusive. Let's differentiate between inclusive and exclusive. So that one can be exactly 0. So if it's inclusive, we don't use this bracket. We're going to use a square bracket. Square means inclusive, okay? But then exclusive, can it ever be infinity? No, it cannot be. No, it'll never reach infinity. It'll try. Infinity is it keeps on going, okay? So on that, we use the exclusive bracket. Like for example, there's another idea here as well about circles, open circle and closed circle. Closed circle means it's inclusive. Open circle means it's exclusive. Now look at this. If I were to ask you, what is the domain of this function? Again, domain means the possible x values it can take. It doesn't go on forever, this one. It's restricted. I'll give you this, okay? The domain of this, again, just look at the x values, right? It starts here. What's the x value there? 1. Where does it end on the x?
5.
5, right? Is it a square? Is it inclusive at 1 or not? Closed circle like this one means inclusive. This means inclusive, okay? So we would use a square bracket there. But on the other side, is that inclusive? No, it's not. Open circle means exclusive. So we would use a normal bracket. There you go. The domain of this function, we don't know what it is. Well, it's a straight line, so it's going to be something like y equals mx plus b, but it has restrictions. What about the range? Tell me the range of this function. Range means the possible y values it can take.
3 to 6.
Right, 3 to 6. Is 3 inclusive?
Yes.
Yes. So you put a square bracket there, and then you put a normal bracket on the other side. It looks a little bit wonky, but that's the notation, okay? Inclusive, exclusive. Cool.
Okay.
What else can we talk about? We can talk about x cubed. X cubed is, this is the parent function, okay? This is positive x cubed. But if you remember from last time, it can have, the degree is 3. The degree is 3. We'll call this number n, okay? We'll call the degree n. The maximum number of turning points is, what's the formula for turning points?
N-1.
N minus 1. So for this case, this cubic function, we can have 2 turning points. So this is the base function, okay? This is the base function. This is y equals x cubed. But you will not get this, like, it's not going to be that simple. The base function is just something you can compare it to. Usually you're going to get something like this. So the equation of this will probably be, well, it's going to be a positive anything. We don't, it's gonna be this one, the equation of this. Something like that. And this is a kind of function that you'll see. You'll rarely see something just x cubed. But we can compare this with this to see what's going on, right? See, now it has 2 turning points. It's an odd degree function. The domain and range, both of them is negative infinity to positive infinity. On the x, it goes forever. On the y, it also goes forever if you follow this and extend it. Another thing that we talked about is, don't worry, we're gonna do some more questions, but this is just a recap. We talked about the difference between odd degree, right? Odd even degree versus odd even functions. They're not the same thing. They're not the same thing. Here, let me tell you what the difference is. Odd even degree just means x1, x3, x2. This would be an even degree, right? Just look at this. x6 even degree, x 1,000 even degree. But an odd function is something that is reflected around the origin, like something like this, like x cubed is an odd function. You see whatever's down here, it's reflected diagonally over here. So the quadrant, it flips, right? So this, it starts off in the third quadrant, and then it ends in the first quadrant. You see that? So if you have something like this 3 to 1, that's an odd function, okay? That's an odd function, but it doesn't have to be a polynomial. That's the thing, it doesn't have to be a polynomial. Could get something like this. This is not a polynomial. See this? This is something called an even function. Why is it an even? Because there's a mirror on the y-axis. Okay, this one is an even function. So whatever you have in quadrant 2, you have the same thing in quadrant 1. That's even function. And then odd is 3 to 1. It doesn't have to be 3 to 1, though. It could also be 2 to 4, something like this. You see, whatever we have up here, you have down there. Is it an odd function or an even function?
Odd.
Exactly, it's an odd function, okay? So just because something has an odd degree, like let's say 4x3, like the previous example we're doing, something like this, okay? Just because the degree here is 3 doesn't mean that this function is odd. It is an odd degree function, but it is not an odd function. If you draw this out, you'll probably get something like this. Is this an odd function? No, it's not. Even though it's an odd degree function, it is not an odd function because it's not symmetrical about the origin. Okay?
Okay.
Then x3, x4 here, look at this. x4 is just like x squared. Again, this is the base function. You'll never see this. But it's the exact same thing as x squared. It's a little bit fatter. What you will see is something like this. You'll see a w. Now, what's a possible equation of this? It's probably going to be 4x4 plus 3x3, yada, yada, right? All the way down to the number. Notice how the degree goes down one step at a time. So this could be a possible equation. You're gonna get this instead, okay? Gonna get this instead. And the domain for any polynomial is negative infinity to positive infinity, but the range, because this is an odd degree polynomial, the range is gonna be different, right? The range, you're gonna need the minimum or the maximum value. Does this function have a minimum or a maximum? Is this vertex a minimum or a maximum?
Maximum.
No, it's a minimum, right? The y value, let's say the y value there is -3 or something, yeah? Can it ever be -4? No, it cannot be. It can be -2, it can be 10, it can be 100, but it can never be -4. That's a minimum. When something opens up, it has a minimum. Think about quadratic, same idea. Something opens up, you see this vertex is a minimum, okay? Maximum would be if it's opening downwards. Like that would be a maximum. So if the leading coefficient of a degree 4 polynomial, let's say something like this is an m, right? It's a degree 4 polynomial. How do I know it's a degree 4? Because it has 3 turning points, and if you do the math, so turning points is 3, that means the degree is 3 plus 1, 4. If the leading coefficient is negative, like it will be in this case, right? Because it's opening downwards. You see that point, is that a maximum or a minimum? Let's say that's 10, right? That's 10. Is 10 a maximum or a minimum?
Maximum.
Exactly. It'll never be 11. So if the leading coefficient is negative, you get a maximum. If the leading coefficient is positive, you get a minimum, right? For even degree functions. For odd functions, it's negative infinity to positive infinity. Okay? Okay, now let's actually jump in here and do some actual questions. Here, tell me this one. What's the degree of this function? See this one? What could be the potential degree?
4.
Exactly. Opening up or down?
Down.
Down. So that means the leading coefficient is gonna be negative, right? So A must be B. Okay, like that. Like C, if you look at C, this is also a degree 4 polynomial. We did this last time, this question. This has a minimum here. It's opening up. So it's a degree 4 polynomial opening up. Leading coefficient is positive. The C, the answer for this is this one, D. Okay, let's make things a little bit more difficult here. Sketch the graph that satisfies these conditions. Just because a quartic polynomial can have quartic, by quartic I mean x4, okay? It goes like cubic, quartic, and then degree 5. We will rarely deal with above degree 5. Degree 5 is called quintic. So this one's degree 4, it's a quartic polynomial, even degree polynomial. Just because it can have a turning point of 3, right? Maximum number of turning points is 3. It doesn't have to have 3 turning points. Like a quartic polynomial could look something like this. See this? It only has 1 turning point. That's not a turning point. It has to have a minimum of 1 because it has to bend, right? Even degree, they have to bend and go back 180. But they don't necessarily have to have 3, okay? They could have 3, or they could have 1 or 2. Let's look at this question. Degree 4, so we know it's a positive leading coefficient, so we're going to start here and end here, right? 3 zeros and 3 turning points. So what could a possible graph look like for this guy? Very simple question. We've done this a few times now, something like this. Actually, that's wrong, right? Because this one doesn't satisfy one of these conditions. Which one does it not satisfy?
The 3 zeros.
Exactly. How many zeros does this have? This has 4 zeros. So we need to change this a little bit. Any ideas on how to fix this? We could do something like this, right? We could do something like this, but then this one only has 2 zeros, right? So over here we've undershot it, over there we've overshot it. So how do you actually fix this? It's a little bit tricky. What you need to do is you need to make a quadratic on the x-axis. Like right here, you need to make a turning point right there. See,
Oh.
now it has 1 0, 2 zeros, 3 zeros, and also 3 turning points.
Mm-hmm.
Okay, so that's the trick. Okay, quartic
Okay.
4, just because it's a degree 4 doesn't mean it, again, same idea. Just because it's a degree 4 doesn't mean it has to have 4 zeros. It could have 4, but it could also have none. Or it could have 1, right?
Mm-hmm.
How could it have 1? 1 is going to be tricky, isn't it? 1 is again the same idea. It's going to look something like this. If it has only 1 0, it's going to look something like this. See this? This is 1 0. 2 zeros would be something like a W. See that? Or
Uh-huh.
another example of 2 zeros could be something like this. Actually, no, that's not going to work because it has to come back A. You can either have a W. That's basically 2, 3 zeros. We just did it, and 4 zeros is the easiest one of them all. Okay.
Okay.
Here, I'm going to ask you to do something. Press the escape button, and you'll see on the Zoom meeting controls where there's like chats and yada yada, right? Mute chat, whatever. You'll see something called annotate. If you don't see it, you want to click the 3 dots that says more. Annotate.
I still don't see it.
Is it on the 3 dots? Did you click the 3 dots more?
I did. It's not there.
So there's it's like a pencil icon.
No.
Should be somewhere. Maybe you're on an iPad. Let me check. I don't know how it works on an iPad. Can quickly double check this. What do you see on that options menu?
There's only chat and meeting settings and disconnect audio.
That's not good. Can you try drawing something on this? Just, I know you have an iPad, just scroll something. Let me see if I can see.
No.
Okay, we're gonna do something else then. It's okay. That's why we're here, right? Okay, try drawing it here. Just draw something. Yeah, there we go. Okay, so you're gonna do this next question, which says, what did it say? Can I not put that in here? I can just give it to you. So we're looking for, okay, we're looking for degree 4, negative leading coefficient, 2 zeros, and 1 turning point. Try drawing this, and you're gonna have to kind of use your head a little bit.
Wait, repeat that?
It's right here. Negative leading coefficient, degree 4, 2 zeros, and 1 turning point. Can you see that or no? Can you see my
No,
writing there? Okay, wait a
I
second.
can't.
I need to use this guy's pen. It's okay. Let me just grab this pen. This way we can both work together, right? So negative leading coefficient, degree is 4, okay?
Mm-hmm.
2 zeros and 1 turning point. So these are the conditions. I'll give you an axis if you want. I'll give you a hint. Negative polynomial means it's gonna, well, you know what to do.
It's gonna open downwards.
Yeah, it's gonna open downwards. It's gonna have 2 zeros and 1 turning point. Try drawing it, see what it could potentially look like.
Is it just like this or something?
Okay, so yeah, actually that's perfect. That's exactly what it is. Okay.
Okay.
Okay, here's another one. Degree 4, but now there's a positive leading coefficient, okay? And there is 1 0 just 1, 0, but 3 turning points.
Um, huh?
Any ideas? Just 1, 0, but 3 turning points. I'll give you a hint, okay? It's gonna touch, it's gonna be like a quadratic. The turning point is on the x-axis. One of the turning points where the 0 is on the x-axis. One of the zeros is right here. See that? You see this?
Yes.
So that's how you do this one, okay? 1, 0, there's only 1, 0, but it satisfies the other conditions, yeah? Okay, here, again, you're gonna have to think, right? That's the whole thing, because it is tricky, I'm not gonna lie, it is tricky, but gonna have to sometimes maybe even think outside the box. Here's one more, okay? Degree 3, okay? Degree is 3. It's a negative leading coefficient. It has 1, 0, and it has 0 turning points. Try this.
So no turning points.
Yeah, no turning points, 0 turning points. What could that look like? It's just the baseline function. It's just the baseline x cubed. The parent function x cubed, but it's negative. That's it. Remember what that looks like? Draw it if you remember what that looks like.
Is it just a line?
So it's a degree 3, right? It's not gonna be just a line, but yeah, it's gonna be one line. Yeah, this is the baseline x cubed, but this one is positive, okay? What's the negative baseline x cubed? Draw that. Negative
Do I
means,
start on top?
yeah, you start on top. You go from quadrant to, yeah, exactly. But yeah, there you go. That's it. 1, 0 right there, no turning points, yeah?
Uh-huh.
And then here's one more. This one, I'm not gonna give you any hint. Degree 3, okay? It's okay, just draw it. If you're wrong, you're wrong. It's positive leading coefficient, 2 zeros, and 2 turning points. Positive means it's gonna start here and it's gonna end up here. 2 zeros, 2 turning points. What could that look like?
Um,
Yeah, perfect. There you go.
okay.
Here's one more last one for this question. It's fun, right? Once you get a hold of it, it's pretty it's a challenge basically. So you kind of have to think a bit. Degrees 4. There are 2 zeros. There are 3 turning points. But now we're gonna add something else to this. There's a restriction. There's a restriction on the range. The range is only from negative infinity to positive 5. Oh, positive 5 is inclusive. There you go. Here's a hint. The range tells you whether it's opening up or down. The range tells you if the leading coefficient is positive or negative. What do you think? Is it opening up or down? Is this a maximum or a minimum? The 5 there, is that a maximum or a minimum? It is a maximum, right? How do you know it's a maximum? Because it can be anything from negative infinity to positive 5. Maximum means what? It's opening downwards. All right?
Mm-hmm.
Maximum means it's opening downwards. So try drawing this. Leading coefficient is negative, 2 zeros, 3 turning points. And all you have to do is to just make one of the maximums at y value of 5. That's it. There's a million different ways to draw this. Actually, there's an infinite number of ways to draw this.
You do it.
I do it? Okay. So 2 zeros, a negative leading coefficient means we're down here, yeah?
Mm-hmm.
We're gonna end up down here. 2 zeros go up once, come down, boom. And we can just say this point here arbitrarily is 5, and you're done.
Oh, okay.
Okay, was it hard?
No.
No, right, it's not that hard. Okay, let's go back to the other one where I can, where's my book? I don't know where it went. Okay, here it is. It's pretty, it's tricky. I wouldn't say it's hard, but it's a very simple, like 10-second problem. If you know what to do though, that's the thing, right? Here, let's look at this. What does the A there stand for? See that A there in blue? What does that stand for? 10 points if you know what that stands for.
What's the second letter?
P. There's another P after that. And then there's an L.
Application.
Right, it's application, okay. So what's going on here? The mining town of Brighton was founded in 1900, okay. Its population Y in hundreds. It's modeled by this. What was the population in 1900, it says? Which is just a fancy way of saying the initial population. What's the initial population? What is the y-intercept? Another way to think about it. Any ideas to any of those? You know how in a linear function, y equals mx plus b, your y-intercept is the b value? Same thing applies to any function, right? Same thing applies to any function. You see, the y-intercept here is 5, right?
Mm-hmm.
So what's the y-intercept here?
7.
7. So what was the population in 1900? Was it 7?
700.
Good, it's 700, right? Not just 7. Based on the equation, describe what happened to the population of Brighton over time. All right, so for this one, what do we know? What's the degree?
4.
4. What's the leading coefficient, positive or negative?
Negative.
Yeah, it's negative, right? It's negative 0.1 if we're interested in. So a degree 4 polynomial that's a negative means it starts and ends where? Which quadrant to which quadrant? Negative degree 4 polynomial. Which quadrant does it start in? 1, 2, 3, 4.
3.
It starts at 3. Where does it end?
4.
4, right? It starts at 3, ends at 4. Yeah, we don't know how many turning points that this has, but looking at it, again, this one's arbitrary. It could have 1, it could have 3, it doesn't matter. That's not the point, okay? That's not the point. Boom. Let's say this is what it looks like, okay?
Mm-hmm.
What does the axis represent? Well,
Um,
read this, read this. X is the number of years since 1900, yeah?
uh-huh.
Can number of years be negative?
No.
No. So that means we can just kill off the negative x-axis completely. What does the y-axis represent?
The number of people?
Can the number of people be negative?
No.
No, so we can kill off the negative y-axis as well. Now describe the trend that you see. What's happened to the population? As time went on, yeah? What happened to the population?
It peaked and then it went down.
It peaked, went down to where?
0.
0, exactly. What happened to the population? It peaked and then it died. The town died. It ceased to exist, right? Which makes sense. Like if you think about it from a historical point of view, mining towns were common during the gold rush, basically. One time that was common. The other time was when we were super dependent on coal. We're still dependent on coal. I know, like we have made some strides, but there's a couple of countries where coal is their main source of energy. It doesn't apply to Canada. I'm talking like China. China is a big user of coal. And there's a lot more countries like that, especially in Asia and Africa. So yeah, Brighton, well, sounds like an English sounding name, right? Probably somewhere in Canada. Not a big user of coal. The town died out, or people moved away from it, right? That's you can write an essay about this. I know this is a math question, but can kind of, it's always good to peek behind the curtain to see what's actually going on. Alrighty, so let's move on to a new section. Okay, a new section. This is, again, this kind of builds off from quadratics, right? If you remember x squared, what's a good one? 5x plus 6. How do we factor this? We're going to use the man method, right? What does it multiply to? What does it add up to?
Um,
So it's like this, ax squared plus bx plus c, okay? It's like this. It's going to multiply to a times c, and it's going to add up to the b value. So what does it multiply to here? Compare these two, right? Get your a and your b's and your c's. What's our a here?
1.
1. What's our b? 5. What's our c? 6. So what's 1 times 6? Because that's what it multiplies to, 6. What does it add up to?
5.
5. What are the numbers? Multiplies to 6, adds up to 5.
Um,
Well, there's only two
3
things that
and 3.
multiply. Yeah, 2 and 3, right? 2 and 3. So once you have those numbers, what do? We are going to break down the 5x into 2x plus 3x, right? 5x became 2x plus 3x. And then we factor two things at a time. What can we pull out from the first two terms?
An x.
Right, what are we left with?
X plus 2.
Right, what can we pull out from the next two terms?
A 3.
What are we left with?
X and 3.
X plus 2.
Um,
You pull out a 3 from 3x, you're left with x. You pull out a 3 from a 6, you're left with 2, right? By pull out, but what does pull out actually mean? It means divide, right? Pull out means divide.
oh,
So if you divide 3x by 3x, if you divide 6 by 3, you're left with a 2, okay? And
okay.
then finally we can jumble this up, x plus 3, x plus 2. This is called the factored form, very powerful. Why is it powerful? What does it give? Do you remember from our quadratic days? These two numbers, what are they? It gives us the x-intercepts, okay? What are the x-intercepts here? And let me tell you, it's not 2 and 3. You have to flip them. Because what we're technically doing is to find the x-intercept, we have to set the y value as 0, right? Like if you look at this, the x-intercept is when the y value is 0, and then you set them individually equals to 0. See, like that.
Mm-hmm.
-3 is one of our x-intercepts, and then -2 is the other. See that?
Uh-huh.
So why is factored form powerful? It gives us the x-intercepts, which is what we're going to be concerned about most of the time, among other things, right? X-intercepts, vertex, y-intercept, those are the three things we're concerned about. Well, y-intercept is given in the question. Vertex, you can, well, we're not interested in finding the vertex in this course, in this chapter, because like when we talked about before, right? Quadratic, we can pinpoint the vertex because the vertex is always going to be dead center between the two x-intercepts, you see? The vertex is right in the center. But when you talk about higher degree functions like degree, like quartic, like degree 4 or something, you see this for the purposes of this course, actually, even in this course, not just for us, we don't care about where these are. We just need to show that they exist, but we don't care about where those are, because finding that is going to be another demon altogether. We could find it, but it's not easy. You have to use a type of mathematical field called calculus to find out where they are exactly, okay?
Okay.
That is grade 12. Actually, I don't know. It's grade 12 here in Ontario. I don't know about it in BC. It should be the same. But we learned this stuff in like grade 10, 11 in Asian countries, China, whatever, India. We'll learn it earlier, okay? But here,
Mm-hmm.
it's a little bit easier, I guess. You'll learn it in grade 12. Only then, only using techniques learned in this course, can we pinpoint where those are. So for the purposes of this course that we're currently doing, we don't care about where they are, all right?
Okay.
But what we do care is the x-intercept. They're gonna be very, very useful here, or that's gonna be our main goal, finding the x-intercepts. Not so much the vertex. The vertex we're only concerned with for quadratics, and it's easier to find. The vertex finding here is gonna be difficult. All right, let's look at, so that was for quadratic, right? We got something like x plus 3, x plus 2 for that function that we are looking before. So it gives us the x-intercepts. You just have to flip the sign, okay?
Mm-hmm.
Now let's take it up one more level. I'm gonna give you a cubic function. You see, boom, there you go. This is a cubic function. How do we know it's a cubic function? You can pull out 1x from the first bracket, 1x from the second bracket, 1x from the third bracket. What's x times x times x?
X to the power of 3.
Exactly, x to the power of 3. Can you tell me where the x-intercepts are for this cubic function? Just flip the sign, flip the sign. They're at -3 from the first one. Okay.
-2.
-2. What about the third one?
Just 3.
Just 3. There you go. 3 x-intercepts right there. Easy as that, right? We can also make it a quartic. We can make it a quintic. It's the same idea, right? So this one has -4 and +5. There you go. Those are the x-intercepts. Just flip the sign.
Okay.
I'm going to throw a curveball at you because that's just how it is. Because I am mean. Well, I'm not mean. I just like to. I don't know. Now this one, the first x-intercept is at 3. The next x-intercept, where is it? And let me tell you, it is not at -6 or +6. Well, it should technically be -6, but it is not there. Where is it exactly? And it is not at -6. What does the x-intercept technically mean? It means when the y value is 0, yeah? When the y value is 0. You want to know where the 3 came from? Because we said x minus 3 equals 0. Add 3 on both sides, x equals 3. So you'd have to do the same thing for the other bracket. Okay?
Uh-huh.
If you do that, where's the x-intercept actually?
Do you divide 2 first or
No,
subtract 6?
no, no. So you want to use the opposite BEDMAS when you're doing this, right? Like go this way. So the question is between dividing or adding. You do addition before you do division. In this case, you'll subtract 6 from both sides first, right?
Mm-hmm.
And then you divide by 2. This doesn't always work. It works like 99% of the time, but there's sometimes this doesn't work. The way to actually think about it is whatever the x term is, you want to save this for the last, okay?
Okay.
Save it for the last. So in this, you would subtract 6 first and then divide it by 2. So there you go. So technically this, the x-intercept here is at 3 and -3. -3 from the second bracket, okay?
Mm-hmm.
So if there's no leading coefficient, you can just flip the sign like we did here. But if there is a leading coefficient, you have to flip the sign and then divide by, or you can just turn it into a linear equation. Cool?
Okay.
So now the question is, how do we actually, because it's not that's going to be our main goal, right? We want to end at this level. We want to end like something like this. But they're not just going to give this to you. What you're going to start off it is going to be something like 2x cubed plus 3x squared plus 5 or something. You're going to start off with something like this, and then you have to factor that into this. This will be the final step.
Mm-hmm.
How do we do that? Let's see what they have for us. Let's go one by one, okay? So these initial questions, they have given it to us. They're nice. But I'm telling you, eventually, your goal on the exams especially, they will give you the big function, the fat one, and then you're gonna have to trim it down like they did here. Sketch a possible graph of this function. We're interested in 2 things, or actually, I guess, a bunch of things. Let's make it 4 things. What is the degree of this function? What is the leading coefficient? What are the x-intercepts? And what are the y-intercepts? We don't care about the vertex in this course because that's very hard to find. So tell me, look at this. What's the degree of this function combined? What do you think?
Is it 3?
It is not 3. I know you would say 3, it is not 3. Think about it this way. How many x's can you pull out from the first? You can pull out an x. Second one, how many x's? 1. How many x's from the third one?
1.
2.
Oh.
What does that multiply to? x4. So it's a degree 4 polynomial. Cool?
Mm-hmm.
Leading coefficient, just look at this sign here. Positive or negative?
Negative.
Right, -1. Where are the x-intercepts? On this one, there's no leading coefficient inside. You can just flip the signs. There's 3 x-intercepts. Where are they?
-2, +1, and +3.
Right, good. Oh, and here's a new idea. You see this guy has an x-intercept of 3, right? X-intercept
Mm-hmm.
of 3. But this is what you call a double root, okay? What does a double root mean? It's because the fact that it's squared, you see? The fact that it's squared.
Uh-huh.
So when it has a double root, at this x-intercept, there's a turning point. Double root equals turning point. So one of the turning points is going to be at that x-intercept. How do we know? Because of the double root. What does a squared mean? It means a quadratic, right? A parabola. That's the idea. Whichever root is doubled, it's going to have a turning point. Okay?
Mm-hmm.
Whichever root is 1, like, see this one is one root, both of them. That means it's a straight line. I'll show you. All right, last thing, y-intercept. How do we find the y-intercept?
Um,
Think about it. At the y-intercept, what is 0? Something is 0 at the y-intercept.
X.
X is 0, so you just replace all the x's with zeros, right? So 0 means you can just ignore it. So boom, ignored. Oh, the -1 is relevant, but the x is ignored, and this x is ignored. So we have negative times 2 times -1 times -3 squared. What is this equals to?
What does it mean if like the negative sign is outside of the bracket?
Oh, you can just treat that as -1.
-6.
Nope. Hey, look at this. -1 times -1 is +1. You can ignore that, right? What's -3 squared? What is -3 squared?
9.
Yeah, what's 9 times 2?
18.
There you go, that's the y-intercept. All right,
Okay.
so now we can now we can fill in all the dots. Pretty simple. Leading coefficient negative, degree 4 means starts in quadrant 3, ends in quadrant 4, okay? When there's an x-intercept at -2, let's say that's -2, there's an x-intercept. There's an x-intercept at 1, and then there's an x-intercept at 3, like that. And then we know the y-intercept is 18, somewhere up there. And we know at the 3, you see at the 3, what do we know? There is a double root, right? So that means there's a turning point at 3, okay? And now we just join the dots. Again, we're not concerned with, it could have 3 turning points, but it doesn't have to have 3 turning points. So it's gonna go through there, turn, come through the x, and then we know there's a turning point at 3. There's no way it's gonna look like this, because if it looks like that, we're gonna end up with 5 different roots. So the only way this is gonna work is if it looks like this, and there you go. That's a possible sketch of this. And there is a bazillion, there's an infinite number of sketches that satisfies these conditions. Here, let me just draw you a couple. It doesn't have to be like that, right? Actually, no, that one's not gonna work, because like the maximum doesn't have to be there is what I'm trying to show. Like it could be like this, right? And it can come all the way down, and then it can just turn, boom. Just like this, you can make like a bazillion different sketches. Okay, you don't have to be precise in that, but you do have to be precise with the fact that all these characteristics are met in your graph. Okay, do you kind of get this? I'll see what that looked like. Yeah, so they did something like that. But again, this one could be anywhere, right? This maximum point could be anywhere. Now this one's gonna be difficult, because now we're working backwards. So they've given us the zeros, but we have to come up with the equation, okay? How do you do something like this? I'm gonna give you the rubric, which we kind of saw before. It's a cubic, means there's gonna be x minus a, right? X minus b. There's gonna be 3 x-intercepts, x minus c, something like that. And then it's gonna have some leading coefficient k, okay? Like that. We know one of the zeros is -2, so simply plug -2 in there. So it becomes x plus 2, right? What does the second bracket become? Just plug the 3 as b.
That's it?
That's it, x minus 3, right? The third one is a little bit trickier though. The third one is a little bit trickier. It's not gonna be x minus 2 over 5. We're gonna have to work backwards from here. Multiply 5 on both sides. Subtract 2 on both sides. There you go. That's what it is technically. It's not x minus 2 over 5. Okay? When you get a fraction or something, you're going to have to work backwards to see what it actually was. So this is 5x minus 2. There you go. That's the equation. But we also now need to find the k, right? The k, the leading coefficient. We know the y-intercept is 6. What's the significance of that? Why have they given us What does it mean when the y-intercept is 6? What information does it give us? Y-intercept means x is 0, right? So when the x values are 0, what's the y value? 6. That's what it means. Y-intercept means plug x as 0 and y as 6. All right, tell me, what is this equals to just this bit? You can do it in your head if you want, or you can use a calculator, whatever is easier for you. But it's pretty simple. No? It's easier than it looks. All right, here, let me help you. 0 plus 2 is what?
2.
2, right? What's 0 minus 3? Negative 3. What's 5 times 0 minus 2? Well, 5 times 0 is a 0, and 0 minus 2 is negative 2. There you go. It's easy as that. Negative 3 times negative 2 is positive 6. So it's 12. Okay? You see this? What was the issue that you were having? It's pretty straightforward. It's not that bad, right? We're just subtracting. We're just adding and subtracting. If you're not confident, you can always use a calculator. Just plug it in like you see it. But we know that's going to be equals to 12. So we have k times 12 equals 6. Now, how do we solve this equation? It's a linear equation for k.
You divide by 12?
Yeah, you divide by 12. 6 over 12 is 0.5 or 1 over 2. Let's write 1 over 2. And that's it. You're done. K is 1 over 2. Just replace this k with 1 over 2. And that's the final answer. That's the equation.
Okay.
Here, something has a 0 of negative 3 over 4. Okay? What is this in terms of x? If you have to write this in factored form, what would it be? Would it be x plus 3 over 4?
No.
No, it's not going to be that, right? That's a trap. So how do we actually find it? Think of it like this, right? You work your backwards. Why don't you try this? X equals 3 over 4. Work backwards up until the point you get a 0 on the right-hand side. What do we do first? We multiply by 4, okay? So you get 4x equals negative 3, and then you add 3 on both sides. There we go. 4x plus 3 equals 0.
Okay.
Let's try another one. Use the same idea, right? X equals negative 6 over what's a prime number? 11. Tell me, what is this in the factored form? You can use the steps on the left if you want.
Um, 11x plus 6.
There we go. Okay. So 11 plus x plus 6 in the factored form gives you an x-intercept of negative 6 over 11. X-intercept 0, they both mean the same thing. Cool? Alrighty. Now let's do this one. Write the equation of the cubic function below, right? Notice how there's 2 turning points here. What does a turning point mean when it comes to factored form? It means there's a double root, okay? Like for example, if you have x plus 3 squared and x minus 2 or something, this is a cubic polynomial, right? We don't care about the y-intercept here. It's a cubic polynomial. We know one of the x-intercepts, just flip the sign, it's positive 2. We know the other x-intercept is at negative 3. What happens at negative 3? Squared means turning point. There's like a mini parabola here. You see like that. And there you go. Okay, so when there's a turning point, you get a squared. When there's a squared, you get a turning point. So in this question, they've given us turning points, which means we're going to have squares, right? So let's tell me what a and b is here. And there's a squared because there's turning points. What is a and what is b? A and b just mean the x-intercepts.
A is 2.
Yeah.
And B is 3.
So a is negative 2, which makes it x plus 2. B is positive 3, so it's going to be x minus 3, okay?
Okay.
How do we find the k value, the leading coefficient? Notice they've given us a point. It's unclear what the y-intercept is, but they have given us a point. We can use that to find the leading coefficient. We know the leading coefficient is going to be positive, but we also have to pinpoint what it is exactly, yeah? So when x is 2, what's the y value? See, that's the point. When x is 2, what's the y value? 4. Okay? So you have k times 2 plus 2 is 4. 4 squared is 16. Negative 1 squared is just 1 equals 4. So k is 4 over 16, which reduces to 1 over 4. Do you see how we got that? To find the leading coefficient, you just plug in a point, right? Here, last question, we had the y-intercept when x was 0. But here, they've given us a point. We don't know what the y-intercept is. So we just plug 2 as x, like we did in this step, and plug 4 as y. And then just go from there, right? So 2 plus 2, 4. 4 squared, 16. 2 minus 3, negative 1. Negative 1 squared is 1. And then you divide both sides by 16, you get 1/4, or 0.25. So therefore, the equation of this function is, we'll just replace this k with 1 over 4, and you are done. State the domain and range of this function. What's the domain? It's a polynomial function. What do you think? We talked about this in the beginning of the class today. The domain of any polynomial function is what? Domain means the possible x values it can take, okay? It's negative infinity to positive infinity. This is an even degree polynomial, so the range won't be the same. What's the range here? Range means the y values.
Um,
0 to positive
infinity?
infinity. Yeah, there we go.
Okay.
Because it can't go beyond 0, and 0 is inclusive. That's why the square bracket. Okay?
Okay.
Yeah, all right. Let's call it a day there for today.
All right. Thank you.
Bye-bye.